As with any AIME problem 15, this problem looks terrifying. At least we have a diagram. The diagram is also terrifying. Okay, so what we're gonna do first here is we're gonna look at the condition with omega 1 and omega 2, because it turns out this is just, it gives us some small information and then we just throw away the circles, circles omega 1 and omega 2. So what we have is that since their radii are equal, O1b is equal to O1c, and we have that O2a is equal to O2b. And we also have that since omega 1 and omega 2 are tangent, we have that the sum of the radii, or we can say like O1b, O1b plus O2a is equal to 15. Alright, so now we can throw away the circles because they don't give us any more information. And now what we really want to focus on is this cyclic hexagon here. And this is a weird cyclic hexagon, and we need to find the area of it. I don't know if you know this, but finding the area of weird cyclic hexagons is not easy. So we're gonna try to turn this into a nicer cyclic hexagon. And the reason why this cyclic hexagon is weird is because there's no nice properties about it, except for the fact that it has like equal side lengths or something, but even that is not useful. If we want to find the area, we're probably going to have to dissect it into different shapes, like something like this. We dissect it into a cyclic quadrilateral and two isosceles triangles, but it's really hard to do this because we don't know what like BC and AD are, and that seems hard to figure out. Maybe it's not hard to figure out. I need to pursue the solution I read on AOPS wiki. I don't know any other solution. Okay. So what we're actually going to do to make a much nicer hexagon with the same area as this one is we're going to reflect this quadrilateral here about the perpendicular bisector of O1, O2. This may look unmotivated. It probably is. I don't know why we would do this really. I do, but I don't know how I would come up with that. But if we do reflect this about this line, we get a shape that looks like this. And you may think that DC, it looks parallel to B prime A prime, and you're right, and that's what we're going to show. And so now that we've done this, this hexagon has the same area as this one, since reflections don't change the area of anything. So this hexagon is much nicer when we dissect it, and we're going to see why. So firstly, note that we still have from this initial thing, we have that this is equal to this. Do not get misled by the fact that this is O2, because this is like also O1 from original, the original thing. Do you see it? Okay. And then we also have that O2b is equal to O1d. So I'm actually O1c. Sorry, I'm gonna mark these all with the equal side length things. So like this is equal. That's not nice. Okay. We have this, and then we have this. And because of the way cyclic quadrilaterals work, if we have like two opposite equal side lengths, that just means the whole cyclic quadrilateral is isosceles trapezoid. And so we can see here O2A prime O1D is isosceles trapezoid. And similarly, I'm going to use a different color now. Actually, I'm going to use a different color for the whole thing. So we have a isosceles trapezoid here. And similarly, we have an isosceles trapezoid. Wait, no. Whoops. I hate Microsoft Paint. Just kidding. I love you, Microsoft Paint. Okay. And then we have that this is also isosceles trapezoid. Okay. So that's nice. And this shows one reason why this reflection thing was useful. It's because originally we had all the equal side lengths right next to each other, but now we have them apart from each other. If we have them next to each other, we can't make isosceles trapezoids, but when we have them apart from each other, we can. And so notice that these two isosceles trapezoids share a common diagonal, and that's O1, O2. And so in any isosceles trapezoid, its two diagonals are congruent, which means that, wait, I'm going to use some more colors. Okay, so we also now have that this diagonal is equal to O1, O2, which is also equal to this. Wait, oh yeah, I did the wrong color. Okay, whatever. So we have that what we have now is that A prime D is equal to B prime C. And that's good. And that's good because if we now if we clear all this clutter up. Wait, I'm gonna delete all this. Okay, so I'm gonna write this again. Actually, a prime d is equal to b prime c. And that's very nice because now we have shown that, wait, I thought I was using a line. Oops. That was actually a pretty good freehand line. Okay, we have that b prime c is equal to a prime d. So that means now, because of how cyclic quadrilaterals work, that we've shown that b prime a prime cd is an isosceles trapezoid. And that's what we hypothesized at the start. Now we've shown that. And that's very nice because it actually turns out now um, that this hexagon consists of isosceles trapezoid and two congruent triangles, DO2B prime and CO1A prime. So we're actually going to show that right after this. First, let's find the area of DB prime A prime C. Now that we know it's isosceles trapezoid. So looking up here, all the side lines carry over. So we have that B prime A prime is 2, C, D, even though we reflected it, that doesn't change the side length. That's 16, and each of these diagonals is 15 long. And so this is now just a typical thing, typical geometry exercise, which is to find the area of an isosceles, to solve for an isosceles trapezoid given its two diagonals and its two bases. So let's draw that here, and then let's do this. Actually, we won't have to do it here. Let's do it on the diagram that we already have. So from here, we can see, because of the way isosceles trapezoids work, if we draw these altitudes here, these are supposed to be altitudes, we'll have that this is going to be 2 as well, and each of these has to be equal. So we'll call these 7. Well, we know where they're 7. I'm crazy. I've done too many takes. Okay, so we know these are 7 because they're going to be equal, and they have to add up to 16, all 3 segments here, this segment, this segment, this segment. This is not a very good diagram. I didn't make it. And so okay, so we have that this is 15 here. Each of these the diagonals are 15. And we also have that this whole thing here is 9. This is a very cluttered diagram. But the height of the isosceles trapezoid is 12. Okay, so I'm going to draw this now a second time because now this is a messy diagram. Okay. So we have that this is 12. I'm going to make this bigger. Wait. Okay, let's make this bigger here. That's bigger. Okay. So now we have, we know this is 2, this is 2, this is 7. It doesn't look like that, but trust me, it is 7. And then we have, if we draw this line here, we know this is 15. Oh, wait, no, not that. Wrong line, sorry. This is 15. Okay, I'm not good at this. This is 15. So we know that this whole thing is 9. And then we know that this altitude must be 12 by Pythagorean theorem. So that's nice. We have like a 9, 12, 15, 3, 4, 5 triangle there. And so by Pythagorean theorem on this triangle now, on this triangle here, we have that this is root 193. That's a beautiful square root. And this is also root 193. So we've solved for this trapezoid now. So let's go to a big diagram. Let's put what we know. So we know it's diagonal. We'll just draw one of them. We know its diagonal has a length of root 193. Oh wait, no, not that. We know it has a length of 15. And we also know that this is root 193. Let's do that in blue. Root 193. And then we also have that. Well, I'll just do this in black. So we have that this is 16, and this is 2. All right. So we can find the area of our isosceles trapezoid now. That's easy. We already know the height's 12, has bases of 2 and 16. So therefore, by just the basic trapezoid area, the area of trapezoid, area of B prime, A prime, C, D and we know that's equal to 108 by the basic formula. Okay, so now we need to look at triangles DO2B prime and A prime O1C. So we're going to show that they're congruent. So let's write that here. So claim DO2 dot 2 B prime is congruent to dot 2B is congruent to A prime O1. I wish my parents named me this. It sounds like an interesting name to have. Okay. And so we can use SAS basically. So the sides are obviously O2D, O2B prime, O1A prime, and O1C. And so we know, as we already marked before, we know these lengths are equal from the circle thing at the start. This thing here, that goes here. And we also we also know that these are going to be equal because they're cut off by the same arc. A prime C and B prime D are equal, so those angles are equal. So therefore, by SAS, I'm gonna mark this better. Okay, we don't need any line. Those angles are congruent. So we just have to find the area of one of these triangles. So let's find the area of B prime O2D. And this looks like a law of cosines thing. So it looks like we're going to use law of cosines in some way. We don't know what these are, so we're going to set them to A and B. And so by law of cosines, oh yeah, and let's let this be theta. So we're probably going to solve like some system of equations or something like that. So we have that A squared plus B squared is minus 2A B. This is where the handwriting gets bad. Cosine of theta is equal to 193. And we also have from the very beginning, if you remember, that the sum of the, where's my mouse? The sum of the radii is 15, so we have that A plus B is 15. We want to find the area of this triangle, of course, so we are looking for AB. In terms of like the trig that we're already using, we're looking for AB sine theta over 2, which is the formula for the area of a triangle like this, theta, A, and B. Okay. We have 3 unknowns and 2 equations, but it turns out we already know what cosine of theta is. If we look here, this is 180 minus theta because of cyclic properties. If we look at like O2 DCB prime as a cyclic quadrilateral, we have like the thing that opposite angles in the cyclic quadrilateral adds 180. But we already know what the cosine of 180 minus theta is. If we look here, this is 108. We already know the cosine of this because we already have a right triangle there. The cosine is just 9 over 15 equals 3/5. So that's cosine of 180 minus theta. There, equals that. And so therefore, we have that cosine of theta is negative 3/5 by trig. So now we can fill this in. So actually we have a squared plus b squared, and then negative 2 times cosine theta. The negatives cancel out, so we get plus 6/5 plus 6ab over 5 is 193. And now we square the a plus b, because we only need to find what AB is. And we can find that if we just square a plus b equals 15 to get a squared plus b squared plus 2ab is equal to 225. And so subtracting these two equations, we have that 4ab over 5 is equivalent to, why did I say equivalent? Is equal to 32. And so therefore AB equals 40. And now if we go up here, we already found cosine of theta. So we know that sine of theta is going to be 4 over 5. And we know, wait, shoot, what did I just do? And we know that's going to be 4 over 5. It's positive because theta because theta is not more than 180. So sine of theta is 4 over 5. And we know what AB is. AB is 40. So now this is equal to 40 times 4 over 5 over 2. I should once again put that this is the area of O2 B prime D. Oh, this is a complete mess. I don't even know what this is. O2 D B prime is this, which is equal to 16. So the area of this is 16. The area of this, as we found, is 108. The area of this is 16. Adding these all up, we have our final answer of 140. I don't think you understood any of this. Like, just look at this. Okay. I mean, I think this hexagon kind of looks like your mom. As in, like, it has like two congruent opposite side lines. You know, that's what your mom looks like as well.